Welcome back to 8701. So in this lecture and also the next, we want to look at some of the experimental findings of neutrinos. Given the sheer number of experiments and the long history in which we are trying to understand neutrinos and neutrinos' behavior, this can be rather confusing. So I'm trying to condense this a little bit and just give you the highlights of the basic pieces of information. So this one here shows a summary of what we know from neutrino oscillation. So if we look at atmospheric neutrinos, we find that muon neutrinos and anti-muon neutrinos disappear, and they're most likely converting into tau neutrinos and anti-tau neutrinos. We look at accelerator neutrinos. Here we are using muon neutrinos and anti-muons. We can show that they disappear over distances of 200 to 800 kilometers. From accelerators, we also know that they appear or reappear as electron or anti-electron neutrinos over those same distances. From the solar neutrinos, we know that electron neutrinos convert into muon neutrinos and or tau neutrinos. There is more detail to the story than I'm giving you here, where we would have to discuss the interaction, the meta effects of neutrinos. That is for a different lecture. That goes beyond the scope of what I want to discuss here. From reactor neutrinos, we also know that anti-electron neutrinos disappear as well. So the name of the game now is to take all of those pieces of information and extract information about the neutrino's property. And that, in order to do that, one has to make assumption about the number of available neutrino generations, and in some parts of the interpretation also about the nature of the neutrinos. As you can simply figure out of the exercise we had before, it matters to the neutrino oscillation probabilities whether or not one assumes 2 or 3 or 4 neutrinos in the mix. But if you just focus here on 3 neutrinos, we still have the problem that we have degeneracies in the discussion. And they can be boiled down to 2 major kind of trends. One is where the spectrum of the neutrino masses follows a normal ordering, meaning that the mass of the first is smaller than the mass of the second, is smaller than the mass of the third, or that the spectrum is inverted, meaning that the mass of the third might be smaller than the mass of the second and the mass of the first and the second. Data suggests that the difference in mass, the difference squared in mass splittings between those states is such that delta M12 squared is much smaller than delta M31 squared, which is approximately the same size of delta M32 squared. So if we look now at the numbers for the normal hierarchy spectrum, we find that the mass of the first is much smaller than the mass of the second, which is a little bit smaller than the mass of the third. Numerically, we find the mass of the second is in the order of 8 times 10 to the minus 3 electron volt, and the mass of the third in the order of 0.05 electron volts. So really small masses. The inverted spectrum, here the story is slightly different. Here we find that M1 is about 0.05 electron volts, which is similar to the square root of the mass splitting between 3 and 2, which is also 0.05 electron volts. The information of the neutrino oscillation experiment and then how to map into the individual parameters of our neutrino CKM matrix is summarized here and also in the mass information. And I don't want to read the entire table, I just leave this here for you. So in order to understand this, one has to go back to the first slide and understand what kind of information we extract from from various neutrino experiments, for example, the solar neutrino experiments, and then think about, is it sensitive to oscillations between the first and the second generation, or the first and the third generation. So that's kind of the mapping you have to do in order to understand this table fully. There's some experiment where the information just dominates the position of a certain measurement. In others, there's combinations of results coming out The other reason why I put this table here in this lecture is to just illustrate how diverse the landscape of experiments is and why that's needed. In order to get a full picture of neutrinos and their properties, one has to identify the individual properties in the experiments and then put the picture back together in global fits or in a general analysis of the data.